Swayam Prabha. Digital India. Educated India.
Welcome to the week 9 tutorial. We'll be discussing center of mass and center of stiffness, how to calculate center of mass and center of stiffness in this tutorial. Basically, we use the center of mass and center of stiffness calculations when we are dealing with 3D analysis of structures or buildings. So, when we are lumping a mass as single degree of freedom system, there is no change in center of mass and center of stiffness of the structure. But whereas when we deal with 3D analysis of structures, then the torsional effect will be coming into picture. So, in order to verify whether torsion is present in the structure or the building or not, we need to calculate what is the center of mass. I mean to say the location of center of mass and the location of center of stiffness have to be known. So, the difference between these two will give you the eccentricity that is present in the building, and then from that we get to know what are the forces that are acting on the given building to calculate the torsional effect. So, with this introduction we will go into calculating a simple problem where we get to know how to calculate center of mass and the center of stiffness. So, the problem says to calculate the center of mass and center of stiffness for the given building, the plan and elevation of the building are shown in the figure. So, in the plan we have total 4 into 3 12 columns and of two types, C1 which is of size 300 by 300 and C2 which is of size 300 by 350 mm, and the beams are of size 230 by 300 mm and slab thickness is given as 120 mm and grade of concrete is assumed to be M25 and the floor to floor height is given as 3 meters. So, with this introduction of the problem, we go into calculating mass of this one slab. So, in this calculation, particularly this problem, we will be dealing only the slabs for calculating the center of mass. Basically, in a building, we have slabs and beams put together constitute more of the mass of the structure, whereas columns are usually giving more importance to stiffness of the building. So, mass of slabs and beams put together make the mass of the structure. So, assuming that we will be calculating mass of one slab, which is calculated in this manner, MS1. MS1 means I want to denote it as S1, the slab 1, which is of 5 meters by 5 meters, which is given in this plan. 5 into 5 the area, and 0.12 is the thickness of the slab, and 25 is the unit weight of concrete. So, we get 75 kilonewton, which can be converted to 7500 kg. Similarly, for all the slabs, almost every slab in our plan is of same size. So, S2, mass of S2, mass of S3, mass of S4, mass of S5 and mass of S6 are equally calculated in this manner. Into 5 is the area of the slab and 0.12 is the depth of the slab and 25 is the unit weight of concrete. So, for each and every slab we got a mass of 7500 kg. So, similarly, we calculate stiffness as we have already discussed. The stiffness of the building will be usually constituted by the column alone. So, basically we are concerned about the lateral stiffness. So, we go with the lateral stiffness which is resisted by the column. So, KS1 slab for the first column 12 EI by L cube, where E is calculated in this manner 5000 root FCK, where FCK is the grade of concrete, 5000 root 25, which is around 25,000 Newton per mm square, where 25 is the Newton per mm square. So, E is calculated, which is nothing but modulus of velocity, and then I is moment of inertia, because we have two kinds of columns, C1 and C2. For C1 column, B dq by 12. C1 is of size 300 by 300 mm. So, 300 into 300 cube by 12, which is nothing but 300 power 4 by 12, which is coming around 675 into 10 to the power of 6 mm power 4. So, now substituting these two values into the stiffness calculation, 12 into 25,000 into 675 into 10 to the power of 6 by 3000. 3 is the height to floor height. So, 3000 is in mm, 3000 cube. So which is coming around 7.5 into 10 to the power of 6 Newton per meter. This is directly calculated. The result which we got from 12 into the calculation which is shown here will be resulting in Newton per mm, where you need to convert it to Newton per meter, and which is equal to 7.5 into 10 to the power of 6. So we have another column for which stiffness is calculated in the similar manner. E is again 5000 root FCK, which is around 25,000 Newton per mm square, and I is BD cube by 12, for which the type of column 300 by 350 mm size. So 300 into 350 cube by 12, which is coming around 1.07 into 10 to the power of 9 mm power 4. So now substituting E and I values into K, 12 into 25,000 into 1.07 into 10 to the power of 9 by 3000 cube will give you around 11.88 into 10 to the power of 6 Newton per meter. So these are the columns which we have. So if we go to the plan, we have 6 columns of type C1 and 6 columns of type C2. So if I start numbering from here, this is column 1 and this is column 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So the first column where we have C1 type of column, and second column we have C2 type of column, third one is a C2 type of column, and fourth one is a C1 type of column. So similarly for all other frames also we have 5.1 as C1 and 5.8 as C1. So we have K1, K4, K5, K8, K9, K12 as C1 columns, and K2, K3, K6, K7, K10, K11 as C2 columns. So here KS1, KS4, 5, 8, 9 and 12 as 7.5 into 10 to the power of 6 Newton per meter, and KS2, S3, S4, S5, S6 as 11.88 into 10 to the power of 6 Newton per meter. So keeping this in mind, we need to calculate the distance from this origin. Assuming this as the origin, we have slab 1, 2, 3, 4 and 5. So we need to calculate the center of this slab such that the distance between the origin and the center of the slab in both x and y directions have to be calculated for calculating the xc value, that means the center of mass value. So I here denote the x1, x1, y1, and similarly for other slabs. So this x1, y1 will give me the center of the slab 1, S1. So from origin I have 2.5 meters because my span is 5 meters. So 5 meters is the span. So center, because it is a square column, both sides is 5 meters. The center will be at 2.5. So x1 is 2.5 and y1 is also 2.5. Similarly, starting from here to this point, so I have this length as 5 plus 2.5, which will be around 7.5. So this is 7.5 and 2.5 in y direction. Similarly, for x3 and y3, this is the distance. So this will be 5 plus 5 is 10, 10 plus 2.5, which is coming around 12.5. So this is the slab 3, and similarly we calculate for slab 4, where we have different y value which is increasing from 5 to 7.5. This is again 2.5, so all put together will be giving around 7.5. So 2.5 and 7.5, and this location will be 7.5 and 7.5. This one will be at 12.5 and 7.5. So once we get the local center of masses of each slab, we will get to know the stiffness. For stiffness calculation also, we need to know the center of stiffness of the particular slab or the column. So we have total of 12 columns. First column we have 0.15 to 0.15, where we have the plan like this. So this is around 5 meters, and this column is placed like this, which is of size one C1 type of column has a cross section of 300 by 300, which is nothing but 0.3 by 0.3. So this is of type C1, and C2 type of column has 350 mm as one dimension and 300 mm as another dimension. So C2. So when we are calculating at this location, this is origin, and from here we have 0.15, that is 150 mm, and then this is in x direction as well as in y direction, plus 5 mm will add up in calculating C5 column, where this is C5. So this is how we calculate center of the center of each column, 0.15 and 0.15, where for C2 column, where this is C2 column, 0.15 and 5.18 is the in x direction. Similarly for all other columns. So in calculating center of mass, we have calculated the distance from the origin to the center of slab. So there we calculate 7500 as mass of one slab, and x1 is 2.5 plus m2 x2, which is 7500 into 7.5, plus m3 x3, 7500 into 12.5. These are the values which you have already calculated, plus 7500 into 2.5, plus 7500 into 7.5, plus 7500 into 12.5. This is for 6th slab. And then adding up all the masses together, 7500 into 6, because all the slabs masses is similar. And when calculating y coordinate, we have the same formula, m1y1 plus m2y2 plus m3y3 plus m4y4 plus m5y5 and m6y6 by total mass of the all slabs put together. So y1 is 2.5, slab 1 of 2.5, slab 2 for also 2.5 y coordinate, and slab 3 2.5, whereas slab 4, 5 and 6 have 7.5, which adds 5 and 2.5. So all put together we can calculate x cm of value 7.5 meters from this origin, and y cm as 5 meters from the same origin. So our center of mass, we got it as 7.5 meters and 5 meters. Similarly, we can calculate center of stiffness in the similar fashion. So now x1 is the distance from origin to the center of the column. So k1 x1 is for the first column. Similarly, we have 12 columns. So columns 12 we have. So each column will get one component of k1 x1. So we got a stiffness of 7.5 into 10 to the power of 6 into 0.15, plus similarly for all other columns we get this equation, and by the total stiffness of the structure or the total stiffness of the columns. So 7.5 into 10 power 6 and 11.8 into 10 power 6. So we have 6 C1 columns and 6 C2 columns. So 7.5 into 6 we can also write like that, and 11.88 into 6. So we end up getting a value of 7.68 meters. This is x coordinate. Similarly, we can calculate for y coordinate also. So x1 y1 is a component of first column, and till calculating 12th column k2 y2, and adding up all the stiffnesses from 1 to 12 will be in the denominator. So similarly, we got ys as 5.17 meters. So now as a summary, so this is the center of mass that we got 7.5 and 5.0, center of stiffness as 7.68 and 5.17. So in calculating eccentricity to get a torsional moment, so eccentricity in x direction will give you like this, 7.68 minus 7.5, that means center of difference between center of stiffness and center of mass will give you the eccentricity. So if it is in x direction or y direction, any of the directions we can find out. So 7.68 and 7.5, you result up at 0.18, and 5.17 and 5 you will get as eccentricity in y direction as 0.17.